So this is the first video of chapter 11, and chapter 11 is on the modern atomic theory. And this first video will focus on light and electromagnetic radiation. So the modern atomic theory focused more on what electrons are doing in the atoms, where they are and how they behave within the atom. And the modern atomic theory has been able to explain more about why elements form certain types of ions. It can explain why helium, for example, is a noble gas and inert, and why hydrogen is so reactive in comparison. Because both helium and hydrogen are small atoms, but and both gases, but one is very stable and the other one is very reactive. So the modern atomic theory is helpful to explain that. And it also explains why these elements fit into certain areas of the periodic table. So we know after the Russian Mendeleev, the Russian chemist who found that when elements are arranged in order of increasing atomic number, certain sets of properties reoccur periodically. So Mendeleev is the one who wrote the periodic law that says that. And by placing the elements that were already discovered at the time, by putting them together per sets of properties, he started to build the periodic table. And so more scientists tried to explain more of the atom and try to devise models of the atom. And the first one was Niels Bohr, who tried to make a new model of the atom, and that's called the Bohr model of the atom. But it was not enough because it only applied to the hydrogen atom. So more scientists worked on the modern atomic theory, and that's how the quantum mechanical model was born. So many scientists worked on it. What is in common in both models is that they looked at how electrons exist in atoms and how they affect the properties of the elements. And they used light to make their observations. So interaction of light is involved in both models. So because of that, we will look at what is light, and we will use this crash course to introduce you to what is light.
Hey, Phil Plait here, and this is Crash Course Astronomy. In last week's episode, I mentioned that nearly all the information we have about the universe comes in the form of light. But how does that light get made? What can it tell us about these astronomical objects? And honestly, what is light? Here's a hint.
One diaphragm for mankind.
Light is a wave. It took centuries of thought and experiments to figure that out, and to also figure out that, at its most basic, light is a form of energy. It travels in waves, similar to waves of water in the ocean. Except with light, the things doing the waving are electric and magnetic fields. Literally, light is a self-contained little bundle of these two fields intertwined. That's why we call light electromagnetic radiation. The details of this are very complex, but we can make some pretty good overall observations about light just from thinking of it as a wave. If you're floating in the ocean, you'll move up as a wave passes you, then back down, then back up again when the next wave rolls by. The distance between these crests in the wave is called the wavelength. Since light is a wave, it has a wavelength as well, and this may be its single most important feature. That's because the energy of light is tied to its wavelength. Light with a shorter wavelength has more energy, and light with a longer wavelength has less energy. And our eyes have a really convenient way of detecting these different energies. Color. What you think of as the color violet is actually light hitting your eye that has a short wavelength. Red light has a longer wavelength, about twice the distance between crests as violet light. All the colors in between, orange, yellow, green, blue, have intermediate wavelengths. This spread of colors, wavelengths, is called a spectrum. Over millions of years, our eyes have evolved to detect the kind of light the sun emits most strongly. Well, that makes sense. That makes it easier for us to see. We call this kind of light visible light. But that's just the narrowest sampling of all the different wavelengths light can have. If light has a slightly shorter wavelength than what our eyes can see, it's invisible to us, but it's still real. We call that ultraviolet light. Light with shorter wavelengths than that fall into the X-ray part of the spectrum, and light waves with the shortest wavelengths of all are called gamma rays. At the other end, light with slightly longer wavelengths than the reddest color we can see is called infrared light. Light waves longer than that are called microwaves, and those with the longest wavelengths of all are called radio waves. These different groups don't really have hard and fast definitions. Just think of them as general guidelines. But together, we call all of these different kinds of light the electromagnetic, or EM, spectrum. And remember, energy goes up when the wavelength gets shorter. So ultraviolet light has a higher energy than violet, X-rays have a higher energy than that, and gamma rays have the highest energy of all. Infrared light has lower energy than red light, microwaves lower than that, and radio waves have the lowest energy. When you look at the whole EM spectrum, you'll probably notice that we really do only see a teeny little sliver of it. Most of the universe is invisible to our eyes. That's why we build different kinds of telescopes, to detect the kind of light our eyes can't detect. They let us see a lot of stuff that otherwise we'd never notice. So you might be asking, how is light made? Well, one of the most basic properties of matter is that when you heat it up, it gains energy, and then it tries to get rid of that energy. Since light is energy, one way to get rid of energy is to emit light. Another important property of matter is that the kind of light an object emits depends on its temperature. An object that's hotter will emit light with a higher energy, that is, a shorter wavelength. Cooler objects give off light with a longer wavelength. You may have seen this in action. Heat up an iron bar and it starts to glow red, then orange, then yellow as it gets hotter. The color, the wavelength of light emitted, changes as the bar heats up. Astronomers use a shorthand for this. We say that light with a shorter wavelength is bluer and light with a longer wavelength is redder. Don't take this literally. We don't really mean more blue or more red, just that the wavelengths are decreasing or increasing. So in this lingo, ultraviolet light is bluer than blue and X-rays are bluer than ultraviolet. So objects that are more energetic, that have a higher temperature, are bluer than cooler, redder objects. This rule of thumb works really well for dense objects like iron bars and stars. Even humans. You emit light, but it's in the far infrared, well beyond what our eyes can see. There are less dense objects in space too, like gas clouds, and the way they emit light is different. To understand that, we have to zoom in on them, way, way in, and look at their individual atoms. And to understand that, we need to take a brief diversion into atomic structure. Atoms are the building blocks of matter. In general, atoms are made up of 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive electric charge, electrons a negative charge, and neutrons are neutral. Protons and neutrons are much more massive than electrons and occupy the centers of atoms in what's called the nucleus. Electrons whiz around the nucleus, their negative charge attracted by the proton's positive charge. The type of atom depends on how many protons it has in the nucleus. Hydrogen has 1 proton, helium 2, lithium 3, and so on up the periodic table of elements. It's common to think of the electron as orbiting the nucleus, like a planet orbits the sun, but that's not really the case. The real situation is fiendishly complex and involves pretty hairy quantum mechanics, but in the end, the electron is only allowed to occupy very specific volumes of space around the nucleus, and those depend on the electron's energy. Think of these like stairs on a staircase, where the landing is the nucleus. When you walk up the stairs, you have to use energy to go up, and when you do, you have to go up a whole step at a time. If you don't have the energy to get to the next step, you can't move. You can be on the first step or the second step, but you can't be on the 1.5 step. There isn't one. Electrons are the same way. They whiz around the nucleus with a very discrete amount of energy. If you give them an additional precise amount of energy, they'll move up to the next energy level, the next step. But if you give them the wrong amount, they'll just sit there. The opposite is true as well. Electrons can be in a higher energy state, up on a higher step, and then give off energy when they jump down. The amount they give off is exactly the same amount needed to get them to jump up in the first place. How do they get this energy? Light. If light hitting the atom has just the right amount of energy, the electron will absorb it and jump up. It can also jump down and emit light at that energy too. An electron can also jump 2 steps or 3 or whatever, but it needs exactly the right energy to do it. But as I said earlier, energy and wavelength are the same thing, and that's equivalent to color. So when an electron jumps up or down, it absorbs or emits a very specific color of light. Not only that, but the steps are different for different atoms. To stick with our analogy, it's like different atoms are different staircases with different heights between the steps. So when an electron jumps down a step in a hydrogen atom, it emits a different energy, a different color of light, than an electron jumping down in a helium or a calcium atom. And this is the key to the universe. Because different atoms emit different colors of light, if we can measure that light, in principle, we can determine what an object is made of, even if we can't touch it, even if it's a bazillion light years away. And we can. Can you tell the difference between these two squares? They're a very slightly different shade of red. Your eye probably can't tell the difference, but a spectrometer can. This is a device that can precisely measure the wavelength of light and can, for example, distinguish light emitted by a hydrogen atom from light emitted by helium. When you hook one of these spectrometers up to a telescope, you can figure out what astronomical objects are made of. In the case of thin gas clouds in space, the atoms are basically floating free, rarely bumping into one another. The atoms emit those individual colors of light, allowing us to identify them. Unlike dense stars, the color of the thinner gas depends more on what's in it than its temperature. And this is how we learned what the universe is made of. Stars and gas clouds in space are mostly hydrogen, with some helium and heavier elements thrown in. Jupiter has methane in its atmosphere, Venus carbon dioxide. Everything in the universe has its own mix of ingredients, like cakes at a bakery. With spectroscopy, we can taste them. But wait!
So what is light? Light is a form of energy. Light has no mass. Remember how I told you that we could classify anything in the universe into two categories, either matter or energy. And so light is a form of energy, and so it's part of the energy categories. Light is a type of electromagnetic radiation. As it was explained in the video, it's an electric field and magnetic field intertwined together and that are propagating. And electromagnetic radiations is made of waves, and they propagate through space like waves move across the surface of a pond. Imagine, for example, you're creating a wave at the surface of water of a pond. You will see the wave travel in that pond and go from where it was created up to the edge of the pond. So every wave has four characteristics that determines its properties. There is the speed, the height, which is also the amplitude, the length, and the number of wave peaks that pass in a given time. So we'll go over each of these characteristics, and we'll start with speed. So all electromagnetic waves move through space at the same constant speed. And that number is called the speed of light, and it's symbolized by lowercase c. C has a value of 3 times 10 to the 8 meters per second. Or in miles per second, it's 186,000 miles per second in a vacuum. So that's the speed of light when light propagates in a vacuum, which means where there is no matter. And that's the fastest value for the speed of light. If you change the medium, if light is propagated, for example, in glass or in water, because the medium is more dense, it will slow down the speed of light. So this value is the value we will use because often it is used for the speed of light in air. The amplitude is the height of a wave. It's the distance from a node to crest or from a node to a trough. So it's the height, of the wave. And the amplitude is a measure of how intense the light is. And so the larger the amplitude, the brighter the light. Waves are also characterized by their wavelengths, and this is symbolized by lambda. Lambda, the wavelength, is the measure of the distance covered by the wave. It's a distance from one crest to the next, or the distance from one trough to the next. So it's the length of a cycle, if you will. It's usually measured in nanometers. And as a reminder, 1 nanometer is 1 × 10⁻⁹ meters. And then finally, the frequency. It's symbolized by nu, the Greek letter nu. And frequency is the number of waves that pass a point in a given period of time. So it's the number of waves or number of cycles that are contained in a given amount of time. For example, on the right here, you have two rectangles containing drawings of waves. Let's say that these rectangles symbolize 1 second each as time passes, and there is only 1 second. And so the top figure shows a low frequency wave because there is only 1, 2, 3 crests in 1 second. So it's a small number of waves per second. So it's a low frequency wave. And then the bottom one with 1, 2, 3, 4, 5, 6, 7 crest in 1 second. And that's, a higher frequency wave. So the units for the frequency are hertz or cycles per second, which is also represented as S-1. And so 1 hertz is 1 cycle per second and is 1 S-1. So you can see that wavelengths and frequencies are inversely related. And this is shown by the formula here. Nu is C over lambda, or lambda is C over nu. Another way to write this is C equals lambda times nu. So the speed of light C is equal to the frequency nu times the wavelength lambda. But the formula as it is written on this slide show how frequency and wavelengths are inversely related. If the frequency is high, the wavelength lambda will be small. As you can see also in the schematics, a high frequency wave has a shorter wavelength and a low frequency wave has a longer wavelength. So how are speed and frequency different? You can see that given the formula above here, or the form that is C equals lambda times nu, you can see that there are two different things. The speed is a constant value, and the value we will use is the 3 × 10⁻⁸ meters per second. And that's the speed of light in a vacuum. But it's usually used also for speed of light in air. The frequency is different for all kinds of lights. And the frequency represents the number of cycles that come per unit of time. So a high frequency wave will have more cycles per seconds, traveling, and a low frequency wave will have less cycles per seconds. So that's how they are different. The electromagnetic spectrum. So electromagnetic radiation can be symbolized by this spectrum. And if you have a white light that you pass through a prism, it is separated in all its colors, and this is called a continuous spectrum. This spectrum is represented here. And what does it mean that it's continuous? It's continuous because there is no gaps or holes. All wavelengths are represented. The adjacent ones are all represented. There is no missing wavelengths, if you will, no holes or gaps. So it continues to go from one wavelength to another without gaps. And so you can see that the electromagnetic radiation varies from very, very small values to very, very large values of wavelengths. What we see with our naked eye is only the part that is called the visible. And the visible goes from violet light to red light. And it's only a small sliver of the electromagnetic spectrum. And on the violet side, if you decrease the size of the wavelengths even more, you go into the ultraviolet, and then the X-rays, and then the gamma rays are on the smaller wavelengths. You see that it's 10 to the negative 12 meters. It's a very small value for the wavelengths. And then on the other side, on the red side of the spectrum, the visible spectrum, if you are increasing the size of the wavelengths, you go into the infrared, then the microwaves, and then the radio waves, with the FM waves being shorter than the AM waves. And so you can see that on the far right side of the spectrum, the radio waves that are the largest wavelengths are 10 to the 4th meter. So the visible part of the spectrum goes only from 400 nanometers to 700 nanometers. So it's a very small part of the electromagnetic spectrum. And so the color of the light is determined by its wavelengths or frequency. That's what wavelengths and frequency tell us about it, about the color or where they are located in the spectrum. And so we observe a lot of white light. And so a white light is a mixture of all the colors of the visible light. It's a spectrum. You see white light because it's made of all the wavelengths, the red, orange, yellow, green, blue, indigo, and violet lights. And all together they add up and make a white light. When an object is absorbing some of the wavelengths of white light while reflecting others, it appears colored. And so that's why we see everything colored, except if you are colorblind. But so the observed color is predominantly the colors that are reflected by the object. So for example, if you have a red sweater, you see it red because that's the color that is reflected by your sweater. And the blue, the yellow, and the green are absorbed by the sweater. Now, if you have a black object, you see it black because it's absorbing all the wavelengths of the light. And so then there's nothing reflected back, and so it appears black. However, something that is white because it reflects all the wavelengths of the visible spectrum and absorbs none. So that's why you see it white.